Hello friends, welcome to the first tutorial session of this course. I am Anirban Santara. I am doing my PhD in Machine Learning and I am a teaching assistant of this course. And in these tutorial sessions, which we will hold one every week, we will discuss the topics that have been covered in the particular week and do a quick summary of all the topics that have been covered in this week, and then we will learn how to solve questions, and these questions will be the ones that you would expect in the assignments and in the final exams. All right, so in this first tutorial class we will be taking the following topics. So let's go ahead. So the topics that we will be discussing today are supervised versus unsupervised learning. Then different kinds of features, categorical versus continuous features. Different kinds of supervised learning problems, regression versus classification. Then we will go ahead to bias variance trade-off, bias versus variance, and we will study how bias and variance they vary with different parameters of the learning algorithm. And then we will study how to control and how to detect and analyze generalization performance of a learning algorithm, So let's first take up the first topic of today's tutorial class, that is supervised versus unsupervised learning. Supervised versus unsupervised learning. So the supervised and unsupervised learnings are two major broad categories of machine learning algorithms. The only difference, so whenever you have been given a question and asked whether a particular learning algorithm has been described, okay, so you have been so there's a big paragraph describing a particular scenario, and you have to identify what kind of learning algorithm is going on in this particular scenario. All right, so the first thing, whether it's supervised or unsupervised, so the first thing that you are going to look for is the kind of training examples that have been presented to you. So supervised learning always comes when, so let me first supervised learning. So in supervised learning, the training examples will always come as pairs. Okay, so these pairs will be, the first term will always be the input, and then you will have the target value. All right, so this is the true value, and this is the description of the present case. So it could be like an image, all right, and the true value may be whether it's happy or sad. So it's already given that this particular image describes a happy face, and so the input examples will always come as pairs of input and target values. So if the target values are given and if you have been asked to predict the target values after looking at the input, then it is a supervised learning problem, whereas in unsupervised learning you don't have targets. So in this case, what happens is you are just presented with input. So the examples, the training examples are just input value, all right, and you will be asked to find some regular patterns or some kind of information you have to predict just by looking at the inputs, all right. So maybe you have a set of smileys like this one or this one, or maybe you have this, you have this one, or you have this one. So just these faces are given, all right, and you have to you don't know. So the information that has been given to you for learning, it doesn't include the information about the kind of gesture that is being expressed through these faces, all right. So you don't know a priori which is a happy face and which is not. So you have been just asked to learn some regularity within this data or find some clusters within this data. So what you will be, your unsupervised learning algorithm, if it is a clustering algorithm, what it will do is it will try to identify groups based on just the appearance of the example. So it will group these two faces together, maybe it will group these two faces together and these three faces in another class, okay, and these three faces together, all right. So this is just based on the visual appearance of the images, right. So it's just based on the input data, not any kind of target data, all right. So say we have been given this kind of a scenario. So this kind of a scenario is described, all right. So this is again supervised, unsupervised, supervised versus unsupervised learning, and let's have this kind of a question, all right. So suppose I have been given 1 million images with their ground truth labels. So I have a huge collection of images, and I know from the data that is given to us. So the data consists of these image and its corresponding label pairs, all right. So say there is an image of a truck and it has been given along with that image that yeah, this is the image of a truck. Then again maybe we have the image of a human face and it has been labeled that yeah, this is the image of a male human face, for example, all right. So the input that has been presented to you is appearing as the data that has been presented to you is appearing as input label pairs, all right. So typical supervised learning scenario, but the problem can be made really tricky, okay. So let's see what comes next. So what I do is, and this is the general practice in machine learning, okay. So whenever you are doing this kind of practical machine learning tasks, so this is what you have to do. So see what we do next. I looked at the data set and found that the images are from a wide range of categories, all right, and there are vehicles, plants, animals, human faces, etc. All right. So what I did is I first did a quick look at the data that has been given to us, and I found that oh my god, the images are coming from a huge variety of classes, all right. So there are all kinds of images. There are images of vehicles, there are images of animals, birds, maybe human beings, and like everything. So it's very difficult to really train one single classifier that would be specialized, that would be able to identify these objects coming from this kind of a wide range of categories, right. This is a really hard learning problem. So I just decided to do a trick, all right, just go a bit different way, different from the a bit more, make the problem a bit more interesting. Okay. So what I decided is, I decided to first go for clustering the images into groups of similar looking objects. All right. So what I first decided is to identify clusters within the image data that has been provided to me. All right. So maybe if I try to, if I ask my algorithm to identify clusters within the data that has been given to me within the images, just the image part. Okay. So maybe it will be clustering all the vehicles together. So all trucks, cars, buses, trains, airplanes, they all come together under one cluster. Maybe all human faces come together in a cluster, maybe all plants go together in a cluster, maybe all animals again move to another cluster. And then once this clustering has been done, then I decided to train one classifier per cluster. All right. So that particular classifier is going to be specialized for that particular cluster. All right. So then I would train one classifier per cluster. Okay. So I can describe the problem graphically this way. So I had this huge data set of images. All right. So these are all images, and first I try to identify clusters within this data. Maybe I have like, I'm just showing 3 of them. Maybe these clusters are like vehicles here, and people, and animals. All right. So these kind of clusters first, and then we would make one classifier per cluster. Okay. Say n. All right. We have n clusters and we have n classifiers. All right. So each of these classifiers will then try to predict whether which particular class that particular image is in. For example, this one classifier would be able to tell me whether the output, whether the presented image is a bus or a truck or a train or maybe a passenger car, or so this way. Second would be like male face, female face, and maybe this is cat, dog, maybe horse. Okay. Okay. So now tell me which part. So there are like this learning algorithm has 2 steps, right? So this is my step 1, where I'm just looking at the images and I'm trying to group them into similar looking classes, similar looking groups or clusters. All right. And in the second step, I'm bringing in the class labels that had been presented to me. All right. So for each particular cluster, I'm going to make one classifier and train it to match the image to the label that has been given to me. So now think for a minute and you pause the video here and try to identify that what are the 2 different classes of learning, that class of learning. So which class of learning is going here, and class of learning, which class of learning is going here. So which part is supervised, which part is unsupervised. Okay. So just pause the video and for a second and try to identify. All right. Okay. So I hope that you are done, and the answer is the first step is an unsupervised learning problem. Okay. So let me write in green. So this is unsupervised because we do not use the class labels here, right? We are just looking at the images, so and deciding. So over here, as we had decided and as we had discussed before, that in unsupervised learning we don't have target values. Okay, so we are not using the class labels over here. Okay, we are just looking at the images and trying to find groups or clusters of images which look similar to each other. All right, and the second step is supervised. I hope you can see it. Yeah, because each classifier will take the images of its own cluster and map them to the target class value of that particular cluster. Okay, of that particular image within that cluster. Okay, so say an image of a car comes over here. Okay, so it's going to image of a car. All right, and that gets mapped to a passenger car. Okay, so this classifier learns this mapping. All right, so this is a supervised learning problem. I hope this makes things clear. So you're going to face this kind of problems in the exam and in the assignment. All right, so let's go and move on to the next topic, which is kinds of features. So we have categorical versus continuous features. All right, so let's discuss what these two different kinds of features are. So categorical features are features that have, so these features, they appear in a finite number of categories or classes. Okay, so for example, gender of a person, okay, then age group of a person, like teenagers or children, that is those who are below say 13, they are children. Okay, 13 to 19 we are teenagers, and then ahead then we have like young people till 35, and then another age group maybe 35 to 60. So we are like working adults, and then above 60 we are senior citizens and all. So these different age groups. Okay, so this kind of features, they are all gender, age group. So these are categorical features. All right, so these appear in a finite number of categories. So this is important. So you can count, you can like have a finite, a fixed n different values which that feature can take. All right, whereas so even presence or absence, okay, of something. For example, maybe you are a doctor and you are looking at X-ray scans and trying to predict whether there is a fracture or not. So maybe there is some kind of feature like a sudden change of intensity. So in the middle of a bone, all right. So you suddenly see that at a particular place there is a black crack noticeable in the white region of the bone. All right, in an X-ray, and that thing. So the presence of that would indicate that there is a fracture. So the bone is broken from in between, in the middle, whereas the absence of that would mean that would not like directly indicate that the bone has a fracture. Maybe there is some other features that would further, like you can carry on the diagnosis using them. So this kind of feature, like presence or absence of something, this is also a categorical features because it can take just two values, right? Presence or absence, yes or no. All right. So these are all categorical features, whereas continuous features, continuous features are those which can take an infinite number of values theoretically, infinite NITE number of values. Okay. For example, age of a person or something, all right, height, theoretically they can take an infinite number of values, weight of a person, then price of something. Okay. So these are continuous features, right? So it's very easy to understand that which one is a categorical feature. It has to take an infinite number of values, and what are continuous features which can take infinite number of values, right? So now let's look into types of learning algorithms. So that is continued over here as well. So types of supervised learning algorithm. So in this you can face this kind of questions in the exam, that these kind of, like a few of these examples will be given, like gender maybe, or age group, presence or absence of something, or height, age, weight. So these things will be given to you, and you will be asked to identify whether it's a categorical feature or a continuous feature. So you should be able to first, like, what do you question yourself? You just question yourself whether this particular attribute, it comes in a finite number of values, a finite number of categories, okay, or is it a continuous value random variable. All right. So whether it's a continuous value random variable or it's a categorical values, it has a fixed number of values. So that, so you go ahead and like check the correct answer, whatever you think is correct. So if it's a finite valued variable, then it's a categorical feature, and if it can take infinite values theoretically, then it's a continuous feature. All right. So next, let's move to the types of supervised learning. And yes, supervised learning, mind it. Okay, regression and classification. Okay. So what is regression? In regression, so it's dependent upon the definitions, they are dependent upon the type of the output variable. All right. So these are dependent upon the type of output variable. All right. And this output variable is what matters. All right. So whenever you are given a problem that whether a certain thing is, so certain learning problem is, certain kind of supervised learning problem is regression or classification, then you have to just check what's the nature of the output variable, whether it's a discrete or continuous. So in regression problem, the output variable or target variable maybe is categorical or discrete, whereas in classification, so in classification the output or target variable is categorical or discrete, whereas in regression the output or target variable is continuous. Okay. So let's take some examples. All right. So classification problems can be like say you have been given images of animals, okay, images of animals, and and they could be either of like images of like I would say 5 animals, okay, and you have to predict like species of the animal or the kind of animal, you can assume. Now, what kind of animal it is, whether it's a dog or a cat or a horse, right? So this is a classification problem because the output variable, okay, you know that it's discrete, okay, it's like 5 different values only, and maybe something given a image of a given image of a tumor, predict cancerous or not cancerous, malign or malignant or benign, all right. So you can see that the output variable is appearing in 2 different, like 2 distinct classes, all right. So it's a classification problem, whereas examples of regression problem could be predict, like given certain features of a car, predict the price of the car. Now the price of the car could be any continuous number, right? So this is a continuous valued variable that is you are going to predict, and it's a regression problem, all right. Or similarly, like the age or weight, height, person of a person, all right, of a person, let's predict. So these all are continuous variables, right, and prediction of these continuous variables from certain attributes of the person is a regression problem, right. So let's move on to the next topic, which is bias variance versus variance. Well, what is the bias of a learning algorithm? The bias of a learning algorithm is a set of erroneous assumptions, okay, in the learning algorithm. And so this particular thing, bias, it's due to the learning algorithm, okay. So it's not due to the training examples that have been given to you. So there are certain assumptions within the learning algorithm which keeps your model limited, all right, limited in its capacity to learn. So that is what is bias, all right. And due to bias, you can miss out important relations between inputs and outputs, all right. So you can see, you can observe that, yeah, there is a very valid input output relationship, but your learning algorithm cannot capture it just because it is not equipped enough, it's not capable enough to learn that particular thing, that particular relationship between your input and output. So that is a bias of your learning algorithm. Whereas variance of a learning algorithm, it's due to sensitivity of your algorithm towards noise, rather I would say model. So the model you are learning towards noise rather than important output or important features of the relationship between input and output, all right. So variance happens when your learning algorithm, it tries to concentrate on unwanted, like or trivial or noisy variations in the data, all right, rather than the important aspects of the data that needs to be captured, all right. And it happens when you have too many features or you have too many too many parameters in your learning algorithm, in your model, or you don't have much training data, so it cannot like really realize what kind of variations are predominant in the data between important, or what kind of relationships between inputs and outputs are actually important, and what actually matters. All right, so it doesn't have enough examples and cannot realize. All right, so let's try to predict how bias and variance varies with, if we vary different aspects of our learning algorithm, and we will study the variation of bias and variance with 3 things. So number of features, number of parameters of your model, and number of training examples. So when you increase the number of features of your learning algorithm, then the bias decreases, because your learning algorithm, it looks at more and more features of the data, and becomes more and more sophisticated. So the bias decreases, whereas the variance increases, because the more the number of input features it looks at, the more is the amount of noise that it gets exposed to. All right, so more it becomes susceptible to, more it becomes susceptible to modeling the noise rather than important features, right? So with the number of parameters of the learning algorithm, so again bias decreases. Why? Because it becomes more and more capable, right? So the number of parameters, as you increase the number of parameters of your learning algorithm, the model becomes more and more sophisticated, and its capacity, learning capacity increases, whereas the variance again increases, because it can use the parameters, the more parameters it got, to model noise more efficiently, whereas with the number of training examples, bias remains constant, remains the same, because bias is not a property that is directly related to the number of training examples that has been presented to the learning algorithm. Rather, it's a limitation of the model, of the learning algorithm, right? So your learning algorithm, your model is not capable enough to learn important features in the data, and that's why bias comes in, and it's not a problem which comes directly from the training data, right? So if you increase the number of training examples and your model remains equally incapable as before, so the bias persists and you cannot do anything, whereas the variance goes down, it decreases. This is because you have variance is coming because like your model is sophisticated, right? It has the capacity to learn, so it was like grabbing on the noise and trying to model the noise, but as you show it more and more data, valid data points, then it learns to really understand what kind of properties occur in general within the data. All right, so what kind of which particular relationships between input and output, they are predominant within the examples, and hence are important to model. All right, so you will be asked how bias and variance of a particular learning algorithm will vary as these different kinds of parameters of a learning algorithm are changed, are modified. All right, and the last thing that we are going to discuss today is generalization of performance. So what do you mean by generalization of the performance of a learning algorithm? The generalization means that how good the learning algorithm would perform when it is presented examples which it has not seen before. So you have a machine learning algorithm and you have got say a million training examples, and you trained it on the million training examples. However, you have no idea of what kind of training examples, what kind of examples it's going to see when it is deployed in the real world, right? So at any time, say you have a machine learning algorithm which is looking at scans of X-rays and trying to, or maybe let's make it more interesting, maybe scans of maybe microscopy images of cells and trying to predict whether there is a cancer or not. All right, and biopsy results and trying to predict whether the result is cancerous or not. All right, so you have trained the machine learning algorithm with a huge number of training examples, all right, but still you don't know in a clinical setting a rare type of cancer or a rare kind of like set of symptoms may appear within the image that has been presented to it, okay, to the learning algorithm, to the machine, to the machine that you trained, all right, and it may mess things up because this particular set of symptoms which is really rare didn't appear in the training example set, okay, so that's why it will fail, all right, in that particular scenario. So what is going to happen in the real world when the system is really deployed is is what really matters, and that's why that's what we mean by generalization performance. So you have a certain training error, right, but and that's let's assume that training error is really small, and so you're confident that your system is performing really great on your training set, all right, but to get an idea about how good it would perform in the real world when it is really deployed, you have to go and check the generalization performance of the learning algorithm. So the generalization performance of the learning algorithm can be controlled by controlling the bias and variance of the algorithm, okay, and that's what you will be taught in the rest of the course. As we go along, we study one model after another, and we will study how to control the generalization performance by controlling the amount of bias or variance, and but how to check the generalization performance. So that's why whenever we have been given a big data set, okay, we make what do we do? We just randomly select a particular section of the data set and we keep it aside, all right, so keep it aside as test data, okay. So we by no means are going to show the algorithm this particular part of the data set that has been given to us, okay. So this particular set of examples will be unseen to the learning algorithm, to our machine, while it is getting trained, and the remaining data set what we had, so we are going to split it again into a validation set and a training set. So the training set is what is used for machine learning, okay, for training the machine, okay, rather I would say that this goes to train the machine, okay. So say after a certain period of training, so say you are doing some like maybe 30 rounds or 50 rounds of training, okay, you're showing the training examples, it's giving outputs, so you're checking the amount of error that has been incurred in that particular episode, and then you're trying to reduce the error by gradient descent or some other algorithm, okay. So after training the machine for some time, you want to go ahead and check that how good the machine is generalizing. So this validation set was held out, right, so it was not being shown to the machine while being trained, so you are just going to train it on the training set, and then this validation set comes in and evaluates generalization, right. So you check how good how the machine is performing on the validation set. So if you see that the validation error is quite high while the training error was low, you can say that the machine is not generalizing, my machine is not generalizing, and so I need to check the learning algorithm, I must train it all over again, because when you are showing some data that it has not seen in the training examples, then it's messing things up. So we go, so like in the entire process of training at regular intervals of time, we stop the training of the machine and then check its performance on the validation set, and this gives us a measure of how well the system is generalizing, right. Now this way we train the machine, okay. So we started from a randomly initialized machine, we trained it on the training set and periodically evaluated on the validation set, and finally we have a machine which has low training error as well as low validation error. So I have a little bit of confidence that the machine has learned the problem really well, and so it is having a small amount of training error, also it's generalizing quite well because it has a small amount of validation error as well. Now as a first, now you must be careful to notice that this validation set was not used for training the system, but it was used to evaluate the system while it was getting trained, right? So, and on the basis of the validation set results, we were going and tuning the learning algorithm just to make sure that the next time the validation error is small. So, in some way the machine has seen the validation data, right, but it must be evaluated to get a taste of the true error that the machine would incur when it is deployed in the real world. We must show it some data, we must evaluate it on this on some data, okay, which it has never seen before, and that's where this test data comes in. So, this comes in and so I'll write here, do final evaluation. So, after the system is completely trained, okay, and it's ready to be deployed, we bring in the test data and we check the performance of the machine on the test data, we check the test error and we report it that yes, this is an estimate of the true error that the system is going to incur when it is deployed. Alright, so the kind of questions that you are going to face from this section is like you would be asked to like say whether the training set is a measure of the true error or the training error is a measure of the true error, right, or whether the test error or the validation error are measures of the true error. So, the training error is not at all the measure of the true error, because it's the error that has been incurred by the system on a set of training examples which it has already seen during its training, alright, and it was improving on that particular set, whereas the test data is completely unseen. So, it's the measure of the true error when it will be deployed in the real world, okay, and the validation set, it gives an estimate of the generalization performance while the system is being trained, alright. So, best of luck, alright, go ahead and solve this week's assignment, and the deadline is 27th of July 11 p.m. Indian Standard Time, alright. So, just go ahead and you will find familiar questions, okay, in this assignment, and solving this assignment will give you a good understanding of the topics that have been covered in this course. So, best of luck, bye bye, see you next time.